Welcome to Homework Lib.
We're going to look at an example of conservation of angular momentum, which is very similar to recoil problems with linear momentum. So conservation of angular momentum, which is usually given the symbol big L. And there are two ways to calculate angular momentum. One is for a rigid, solid object, such as a disk or a hoop or a sphere, as the product of its moment of inertia times its angular velocity. That looks very classical, like m times v, but for rotation. The other way is if you had a point particle of mass m moving with speed v, and it was off the defined origin or pivot point, the angular momentum would be linear m times v times the perpendicular distance between the particle and the origin. So anyway, the situation is this. The idea is you have a kitten that is sitting on a stationary turntable. So we know that the initial angular momentum is equal to 0, so nothing is moving. And we are told then that the kitten starts to move relative to ground. So I'm going to carefully denote the position of the kitten relative to the ground with a marker, a 0 on the ground. And at that point, we'll also have it lined up at a starred position on the turntable, because later on the turntable position will become important for a final question. At any rate, we're asked what happens to the turntable. Well, we must have the initial angular momentum equal to the final angular momentum due to conservation of angular momentum. And why that happens is conservation of angular momentum happens when the external torques on your system are 0 or negligible. And we are told that the turntable is on bearings with very low friction or negligible friction. Of course, with a kitten sitting on those, that could change, but we won't worry about that. So let's write down the conservation of angular momentum equation. But anyway, the kitten is moving forwards in the counterclockwise direction with an angular momentum we can define with mvr. So that tells us in order to have 0, those two pieces to add to 0, the turntable must go clockwise with an angular momentum that we're going to represent with the solid representation. So the turntable must go clockwise. And we can actually determine how quickly it must turn clockwise by solving that equation for the turntable speed. Okay, so mass of kitten times its velocity times the radius is equal to, and here we'll use the disk formula, 1/2 mr squared and that will give us the angular speed of the turntable. Yeah, we could simplify that down a little bit. Drop one factor of radius, get the 1/2 a little bit easier to use. Okay, so we can figure out the speed, the angular speed of the turntable, and mark you, this is relative to the ground. And that is important to note that we are thinking about the ground frame. And the units should be in rads per second. Radians per second is the natural unit for angular velocity. But we can convert to other forms as needed. And we get the turntable angular velocity is 0.556 radians per second. Okay, we're going to ask another interesting question that's going to have us move between frames a little bit. We're going to ask, suppose the kitten walks all the way around the edge and gets back to its starting position. And the way I'm interpreting that is by walking all the way around the edge, it is going to return to the star position. And we're going to ask, where is that star in relation to the O on the ground? So let me carefully ask that question because it involves two frames and an interpretation of what it means to walk around the edge, get to the starting position. Suppose kitten walks all the way around the edge and returns to star. And we ask, where is star in relation to the O? Okay. Well, what we really kind of need is the angular velocity or the speed of the kitten in the frame of the turntable. And what will happen is it must be walking more quickly inside the frame because relative to the ground, that turntable is walking backwards. And we can kind of see this if we imagine after 1 second, where is the kitten and where is the star? So they both started at O, and after 1 second, the kitten is up at point. That's not a very good picture. Sorry about that. Let's get the center in the place where it should be. So after 1 second, the position of the kitten is 0.3833 radians. And we're getting that by figuring out the angular velocity of the kitten relative to ground. And meanwhile, the star has kicked backwards. Not quite as far, but the star is at minus 0.556 radians. So relative to the turntable, let's call this omega kitten prime, is actually the sum of the two angular velocities relative to the ground frame. So walking much more quickly inside of the frame. That's about 1.39 rads per second. and that is with respect to the turntable. And based on this, we can figure out how long it would take the kitten to return to the star. So delta theta prime is 2 pi, and that is omega kitten prime times delta time, using some kinematics here. Rate times time equals velocity, and that time is 4.52 seconds. In the same time frame, we can now ask, where is the kitten in terms of the O? And I should point out the kitten and the star are on top of each other. So at that same time, at t equals 4.52 seconds, we can go back and use the kitten's speed, angular speed, relative to the ground. And we would get 3.77 radians, which is, in terms of a circle, we could draw that 3.77 radians. Let's divide by 2 pi. And it's going around about 60% of the way. So what we can kind of show, kind of a funny picture, but what we would show is kind of a ground picture. The point on the ground has not moved any. Yeah, there's the O. And the kitten has moved a little bit over halfway. So the kitten is here, and it's sitting on top of the star. I'll try to show that underneath the kitten. And that's the picture we have at t equals 4.52 seconds. One final question to address, and that is, what would happen if we had a situation where the Earth is spinning? I'll try to draw the Earth, but we're looking down on the North Pole. The Earth spins from west to east, and it has a certain moment of inertia and a certain angular velocity. And we're going to ask, what would happen to the length of a day if all of a sudden everybody on the Earth, which I'm going to represent for some reason with this blue dot, what if people started moving eastward? Kind of like that kitten picture. Well, hopefully there's not much friction acting on the Earth. We'll assume so. And so we're going to again write a conservation of angular momentum equation and figure out what would happen to the length of one day. If people started running eastward. Okay, don't run into the ocean while you're doing that. So we're going to, again, conserve angular momentum so that the moment of inertia times the angular velocity of the Earth has to equal the final angular momentum and angular velocity of the Earth plus, okay, so both the Earth and the people will be going around in a counterclockwise way if we look down from the North Pole. And again, we'll use both definitions of angular momentum. And what we see is that if we solve for the angular velocity final, we get basically the initial angular momentum will be subtracted from by the people running. Okay, so they will subtract from the initial angular momentum. And what that means is that the angular velocity is going to go down. Okay. So the angular velocity going down, and a reminder that period is the inverse of the angular velocity. So if the angular velocity goes down, the period must go up. And that shouldn't make a large difference. What really matters is that product of the mass of the people times their velocity times the radius of the Earth. And that is going to be minuscule compared to the moment of inertia times the initial angular velocity of the Earth. So not much difference going on.